Welcome to ScalaUA. My name is Borst, and I hope to see you here next year.
Before I start, I want to ask one question. Who here is a native English speaker? Nobody. I myself are also not a native English speaker, and for some reason I find it very interesting that we talk English to each other so that we can understand each other, while none of us is actually native. I do apologize. I only know the word privet. But probably it's best if I talk further in English. I myself started to learn English actually only when I was something like 25 or so, and I was jealous for a very long time about native English, because as a programmer we all program most of the time we program in English. And I thought I had a disadvantage, and it's especially in the more east type of locations, like over here in the Ukraine, that I think that it is actually not a disadvantage to be a non-native English speaker, because in a specific sense I think that we need to think a little bit more about the words which we are using, while perhaps native English people think less about it. It has completely nothing to do with anything that I want to show, but for some reason I just wanted to share it. So let's start. Saving the stack for fun and profit. I don't have any slides. It's going to be a live coding session. Recursion. Probably we all know that with recursion, in general, we can implement any algorithm. But when we run it on the JVM, that algorithm, then sometimes we can have quite big problems. So, for example, if we have a look at this code, the first two functions, even and odd, it's more or less a contrived example. We want to compute whether a list or sequence is of even or odd length, and from even we do that by, if it is empty, we say that it is even length, and else we call the tail on the function odd, so it alterates. We have a specification for that. And with that specification, that should actually work. Even sequence empty, odd sequence empty, even sequence of a specific length, odd sequence of a specific length. And we can have a look at the tests which are then being run, and we see that it works. We see that it doesn't blow up the stack. We see that it has the right answer. But at the moment that we are coding a little bit more, like for example, even 1 to million should be true, and we run it, and we can see that it blows up the stack, and it gives a stack overflow error. It's not even an exception, it's really blowing up. We don't like that as functional programmers, because we want our functions to be pure. Such an error, what is that to a function? Does anybody have any idea?
Side effect.
Check.
A disgrace.
It crashes, it's a side effect. Blows up, it doesn't work. And in functional programming, we try to make those functions pure. We have sort of techniques for that. And anybody has an idea what is a natural technique in functional programming to get rid of side effects? Right. we capture it in the return type. So let's try to do that. Let's say that we have a trait, let's call it pure. Let's say that it takes something. Let's say that it has a result which returns then also this result. And at this moment, we could say that for example, we capture it there. And now on the specification part, Lodex, we could call result back, and on the if we now go to the compiler, we see that it has a couple of errors. The first time is that result needs to be a def. Now the implementation has two specific parts which makes it possible to return a pure, but we have two different type of situations in which we actually need to return a pure. So first part is here. There we should return a pure while we're returning true. Second part is the moment that we do a recursive call. So let's also model that part out. Let's say that we have a done, which takes the result. This moment I don't implement it. Let's say that we have a call. Which will return somewhere in the future pure. And let's say that both return that. Then here we can return done. There we can return call. Now it should be compiling at least. But we're still missing the implementation. So if we go a little bit further, this trait at this moment is not being implemented yet. Let's make it into an ADT. We create it as a seal trait. We create a done, which extends our trait. We create call, which in this case takes a thunk. Is anybody, is a thunk, is that a very well-known concept over here? No? A thunk is something which is going to be called later. So a thunk is something which can be wrapped. It's a function, but it's going to be called later. And we can call it later, for example, this way. If we have an A, we just return the A. But it is a call of the thunk. Then we just want to call it at that moment. And at that moment we can return it. So, for example, if I import here Scala annotation dot tailrec. Now I can prove, or let the compiler prove, that it is a tailrec. And in that case I can call. Implementation then of a done A is simple done which we pass, and pure is the moment that we actually put Thump there. The Thump is going to give us in the end a pure A. Still need to call it. Call Thump and call the result that. And then we see that for even and odd we do not have this side effect anymore. So this only happens on the JVM. On the JVM, this is something which makes that if we jump in between functions, then we can overload the stack. There are other situations where recursion cannot actually be implemented, and we want to slowly build this out in such a way that from the client side, the location where the computation is actually being done, you have as less as possible a footprint with the actual way how we make this function pure. So if I move this whole part over, to a utils class, import utils. Should still work. Yeah, still works. Let's move the specification part over so that we will not capture anymore this, that we capture actually this side effect. And we sort of pulled out the recursive call from the algorithm into a library function, which now is proven to be tail recursive, because we do not execute this algorithm now anymore on the stack, but we move it completely to the heap, and in the heap we build up this representation of the computation at the moment that it is there. So this actually is pretty nice. It is, looks sort of good already, especially if you look at this is almost the same. We made explicit what is the exit case of the recursion, and we make explicit what is a recursive call. And this part is almost the same. There's very little footprint on the client side. Underneath you already see another function that's called the Ackermann function. The Ackermann function is a function which has a very specific property, because it can also not be implemented in such a way that it doesn't blow up the stack. It has a inner recursive call. Ackermann function takes two integers, m and n. If m is 0, we return n plus 1. If n is 0 and m is larger than 0, we return the Ackermann function with other parameters. But if none of those is 0, then we call the Ackermann function, and the second parameter is an Ackermann function itself. And that can also not be implemented in such a way that it doesn't blow up the stack. So let's have a look for that for specification part also. Ackermann function, by the way, is also a very interesting function in more than one way, because it was designed to, with very small parameters, very quickly have very large results. So for example, if we call it with 0, 0, we just get a 1 back. But as soon as m and n are becoming bigger, then very quickly we're going into very huge numbers. So for example, 4 by 1 is the last one which returns a normal integer. Let's add that one. Six, 5, 5, 3, 3. Compiling, and again. Stack Overflow as soon as we have that. So let's see if we can change our library a little bit in such a way that, again, the Ackermann function as it is implemented here, you can see it's basically exactly the specification. As a programmer, very often we need to try to find specifications, but basically I think that we would like very much if we would just get the mathematical representation and we do our work, which is programming, making sure that those type of stack overflows are not happening. So here we match on M and N. We have the case with M is 0 or the case with N is 0. You can see it's almost the same as the specification. Not this one, but that one. And that's how we like it, because we like very much if specification matches very much our implementation. So we want to maintain that in the same format. With an inner recursive call, of course, we could now try to do this, in which case we have a done over there, in which case we have a call here. And now we have a problem, because if over there we now also want to wrap it in a call, an inner of an inner recursive, that would mean that this thing would not take an int, but that thing would also need to take a pure. And we don't want to wrap all our different parameters in such a way that it always is wrapped with a pure. So in Scala we have a for comprehension, and if I take the inner call we'll take it out, and we have the outer call, we can just yield the outer. Now if I change my specification, I need to pass the inner, of course, as a parameter. We get two errors, because in order for the for comprehension to work, it actually needs an implementation of flat map and map. And all the library provided ADTs, if they are using the for comprehension, they have an implementation of map and flat map. So let's do that. Let's go to our utils. We have a flat map, which takes a b and a function which goes from a to a pure of b. It will return the pure of b, and we have a map, also type parameters, which takes a function a to b and also returns a pure b. See what works. Correct. We now need to implement it in such a way. Most of you probably know that map can almost always be implemented in terms of flat map. So let's say that flat map has a function of A, and that we just pass it in the end as done after we have called this function. Because in a sense we are building up a sort of a long list of calls on the heap, and at the end we're done, and map takes an A to a B, returns a pure B. So with flat map we can implement it at the end. The other way is a little bit more difficult. Just like with the result, we can match, and in case that we are done, we're not actually done, because now we still need to have the flat map behind it. So we can rewrite a done in memory in that case, and call A directly on the function, which gives us a pure, and wrap that, and rewrite the done in such a way that it actually is a call, which gives it at the end. The other way is when we have a call itself. Call takes a thump, and a call we cannot rewrite because flat map can be called everywhere in our composition of the function on the recursion. So we don't know exactly where the flat map is being called. It can be called on a call. If we call it on a call, that means that we need something additional to just our representation of call and done. And in functional programming, that's called a continuation. So we're now going to represent in memory continuation. And the continuation, keep in mind, this is all happening at the moment that it's being built up on the heap. And the continuation takes the pure on which we are working, and it takes a function which again goes from A to a pure B. I'm a little bit of a nerd, so let's put that out. It's not an accident that the continuation takes as a function exactly the same as the input parameter from flatmap. And we're building this up at the moment. So if we're going to rewrite it a little bit, we have a pure done of A, which takes that. At the same time we can have a call of a thump which has the continuation, which takes the pure and simply also takes the function which we provide. And the last case is when we are the continuation ourselves. And continuation then needs to be rewritten in another continuation, which takes the continuation of the original continuation, P dot P, and which makes from this continuation a P dot, let me see, F. And that part is wrong, I think. And flat maps over F. So let's see what we've done. When we're flat mapping over a pure, and the pure is done, we rewrite it into a call, in which we call the function from flat map, just passing it its result. At the moment that flat map is being done over the call itself, we simply rewrite it into a continuation, which takes the pure originally, and afterwards put the f behind it, which is the function from the flat map. And in case that we are a continuation ourselves, we take the continuation, we pass it to pure, and after that we pass it a closure, taking an A, call this A on the pure, and then flat map simply the function over it. What you see over here is something which in Scala is being called a pattern match on the type. That actually makes it possible to use that type then in the closure. So we can say that whatever current continuation we're running on, we also pattern match on the type, and we cast then later to that type. Now, of course, we also need to enhance the result a little bit, because this thing can now also be a continuation. Let's say that's a continuation of a pure with a continuation. In that case, we need to match on the pure, which is inside of the continuation. If this is done, we can simply take the continuation, pass it to A, and call result on that. If it's the call of the thunk, we can then take the thunk, call it, and flat map over it the continuation which we have, take the result on that one. In the last case, if we are a continuation ourselves, and in a continuation, then we can take the pure, which is the inner of the continuation. Over that we flat map. Whatever A it provides, we call on the inner continuation, over which we flat map the resulting C, and then recursively call the result on that. Couple of errors.
Typo.
Yeah, thanks.
In line 14 you have a typo in plasma.
That's a typo.
14.
Yeah, this one.
Yeah. That's also a typo. Still have a couple of typos. A1.
Yes, the second was right.
With continuation. This one was just C, right?
Just P.
Just P. No. We have the continuation. The continuation takes pure. We wrap it in the continuation of the pure. Whatever it results as an A, we call on the continuation of the pure, and over that we flat map A. And that one is called F itself. Yeah, that's better. And the reason why it's now taking a very long time is that this Ackermann function takes something like 40 seconds on my machine to completely run through it. But I can see from the fact that it's taken a long time that this part is actually happening. So I'm quickly going to wrap up, because the important thing to take away is that over here it looks exactly the same as the original specification, and that we completely moved out Stack Overflow in almost something like 30 lines of code to something which is completely separated from it, and that's what we like in functional programming. And before I quit, I'll let this run for some time. I want to show you the following, that of course this is not something which is new. This is a technique which is called trampolining, and everything which I showed is actually provided also by the Scala library. And I wanted to show that that's called tail calls. And there we have it. It gives the example, but more interesting, if you go to the code base which created it in the end, it's not the least people who sort of built it up. And from that, an interesting part is if you look at the history of the people who built it up, you can see that Odersky was the first one who implemented it. And he actually implemented it almost in the same sense as that we first did, with just a call and with a done. This was done in 2010. And then if you go up a little bit, you probably know Runorama and Forlone from the functional programming in Scala book, the red book as it is being called. It's quite a famous book and I can recommend it. And that's the moment that they started to add flat map to it, map to it, and exactly the same thing. So 3 years later, we're now talking 2013. And in this, there is still a thing which is not very cool, and that's that the compiler cannot guarantee us this part, where we actually want the compiler to make sure that what with a continuation is being passed is also being rewritten in exactly the same type. So if we then go still a little bit further, we have Paul Phillips, and Paul Phillips was the programmer of the Scala compiler, and he actually did exactly the same thing. He made sure that now also the compiler can guarantee for us that compile time safety in this library is now also being guaranteed. Typically this is not something which you would program yourself, but in the end you can see that in almost something like half an hour you could do it if you knew how to do it, and that it also only takes something like 30 lines of code. More importantly, on the client side, you almost have no footprint. And I thought that was beautifully done by those people, and I just wanted to share that with you. Thanks. Thank you very much.
Sorry, does this approach create the objects of a number proportional to the call depth on heap?
I'm not sure for the continuation, so I would need to see the formula for the continuation. But for the call and for the done, it definitely does. My guess for the continuation is that it does so because flatmap is being called from result itself. So it only creates the continuation actually at the moment that result is being called. If there are no other questions, then I'll leave it at that.
The developer should not be afraid to walk up to people, ask questions, but that's perhaps more a cultural type of thing. So I'm not completely sure if that's really a good thing to say.